Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T, and this video is for Chemical Engineering Thermodynamics 1. We are looking at Chapter 3 in our textbook, which is Volumetric Properties of Pure Fluids, and right now we are looking at ideal gases. In our last lesson, we had seen that for ideal gases in a closed reversible system, for ideal gases, dq could be written as Cv dt plus RT dV over V, or C sub P dt minus RT dP over P. And the work is either minus RT dV over V, or minus R dt plus RT dP over P, depending on whether we have T and V or T and P. Now, what we want to do is look at some special cases. Excuse me. But we've looked at these first three really before in Chapter 2. But if we apply these definitions, Q for an isothermal closed reversible case, if it's isothermal, then dt is equal to 0, and so therefore Q and negative W are both RT natural log of V2 over V1, or, and those are for ideal gases, just as a reminder, or RT natural log of P2 over P1. And if we do an isobaric system, constant pressure, then we'd like to use this second equation here. And in that case, we end up with that Q, sorry about that. Q, write it so you can read it, is delta H, which is just C sub P dt. And for isochoric, we're going to do a similar thing, but looking at this first chunk here. And in that case, isochoric dV is equal to 0, and so Q is delta U, which is C sub V dt. And again, those are for ideal gas case. So our last special case is the adiabatic case. So we're still closed and reversible, and we're going to assume that it's adiabatic and we have a constant C sub P and C sub V. And to do this, we will define a ratio. Gamma is C sub P over C sub V. And if both Cp and Cv are constant, then gamma is constant. Now, we can work with this several different ways, but I have said that it's adiabatic, which means that Q is equal to 0. So if I go back to my earlier relationships, that means that C sub P dt is RT dP over P. Or I also have C sub V dt is equal to minus RT dV over V. And I'm not writing all my little ideal gases on these. Okay. Now, if I take this first equation and divide it by the second equation, I get a Cp over Cv, so gamma is going to be dP over P over minus dV over V. And if you integrate this, or, well, I guess you need to do a step where you gamma times negative dV over V is dP over P. What you end up with is that V1 over V2 gamma, these are for ideal gases, is equal to P2 over P1. Now, they play with this lots of different ways and rearrange this, but one way of writing this is that PV and V raised to the gamma power is a constant. Or if I substitute in different variables, Tp to the 1 minus gamma power over gamma, that's a different constant. And T times V for the ideal gas to the gamma minus 1 power is also constant, yet a different constant. In other words, these are polytropic. So that polytropic process that we derived earlier, now I have an application. And based on this, I know that for gamma not equal to 1, work is R over gamma minus 1, T2 minus T1, or P2 V2 minus P1 V1 over gamma minus 1, or I can just keep factoring and rearranging to get whatever set of variables I happen to have handy. And any of these expressions can be used to calculate work. So adiabatic processes for an ideal gas turn out to be polytropic if the C sub P and C sub V are constant, and therefore I can use these simple relationships for work. Now, one last topic. What happens when we have an irreversible process? Okay, so there are certain things that will stay the same. So for instance, the ideal gas law still stays the same. That's not process dependent. And we've said that for an ideal gas, delta U is indeed C sub V dt, and delta H is indeed C sub P dt. But what's going to change is that the work for an irreversible process or any real process is not going to be equal to negative integral of P dV. Now the problem is it's hard to quantify how not equal is it, okay? And so what we usually do is we say that the work for a real process or an irreversible process is going to be some efficiency times the work of a reversible process. Now this efficiency is a process efficiency and it's going to vary based on the design of the equipment. Now we're going to work a little bit more on this when we get to chapter 5. But for now, we have this definition of a process efficiency, and it allows me to quantify how close to reversible my real process is. So this concludes this lesson. What we need to look at next is some examples doing ideal gas calculations. Thank you very much for your time.